So go a little slower today. So I want to review some core concepts of magnetics. All of this stuff comes out of Maxwell's equations. I don't like Maxwell's equations. I mean, I do and I don't. All right. They're cool, but they're not. All right. I don't want to do divergences, ingredients, and curls and all that sort of stuff. Right. I want to get to this understanding of magnetic circuits and use that to understand how I work with machines to produce forces and create voltages and all that kind of good stuff. All right. So the other day I did mention two core principles that basically drive everything with respect to this class. Right. There were two of them. Let's see if you remember what they were. If I, a wire. Well, if I have a magnetic field and I put a current into a wire in a magnetic field, that wire does what? It moves. All right, that wire moves. And we're going to get into the force production idea later, right? That's what makes a motor work. Okay. What was the other one? If I place a wire into a varying magnetic field, I generate a voltage. Not necessarily a current, but I generate a voltage. All right. And the key thing is I said it has to be a varying magnetic field. So what's varying? The field is varying with respect to time. Okay. If I put a wire into a DC field, meaning it's just, B equal to 4 Tesla, is there any voltage generated at the terminals? No. Faraday's law says you only generate something if you have a changing magnetic field going through some stuff. So let's just review the quick basics of magnetics and Faraday's law and all those others. There's three laws that apply, right? If I have magnetic problems, right? So here's our basics. H and B, right? H is what I call the magnetic field intensity. Okay. So I measure in amps per meter. Sometimes in that I could have Norwegianized that or whatever. The O and the E are supposed to go together. It's Ørsted's. All right. Ørsted was the first person that measured a magnetic field. All right. Sometimes people use that unit when actually designing inductors. As doing inductor design for power electronics, I've used that before. All right. B field is what we talk about the most. It's the magnetic flux density. All right. So if I talk about magnetic flux density, what I mean by that is essentially if I had a surface of some kind, oh man. All right. And I had a field passing through it. B is the density of the field lines going through there. Okay. And if I had this surface here, so this is my surface, what I care about is what's the total flux going through there, which we define, again, I don't like doing the calculus. I don't want to do the calculus. We're not going to do the calculus. B dot dA, right, is the total flux going through there. Now, what is that similar to from, if you remember fields, and I'm sure most of you don't want to remember fields, right? But if you remember fields, what's the parallel that we have if we're talking about charges moving around a circuit? How is that picture where I've got a B going through a surface? How does that parallel something in the circuit side of things? You have a what density in a circuit? Current density, right? You call that J, right? So if I had a circuit, in other words, if this was a wire and I could call this J, right? This would be, it won't let me erase it, all right? If I had this where I had a J coming through here, I would say the total current here is J dot dA, right? We're going to use that later on, right? Basically in this development of things, but basically the current is basically the summation over the area of the current density, okay? It's how fast charges are moving through a surface. In this case, how fast flux is moving through a surface. Magnetic flux is exactly like magnetic current. All right, we're gonna play on that a little bit as we go through the lecture today. All right. So what I have is then flux, or what I defined here as flux per turn. All right. which I'll explain why that is a little bit. So phi is what we write that as. So B and A are vectors, all right? And I'm doing the dot product. If I do a dot product of two vectors, what do I get? A scalar. So phi is a scalar, just like I, current, is a scalar, okay? And for a linear magnetic material, which is primarily what I'll deal with. So the first chapter of the book, and I think also in the other section, he'll talk a little bit more about non-linear materials. I'm not going to focus on those so much. No material is linear. Like a motor, which is made of iron, iron's not linear. All right, but it's much harder to understand that. I want to focus on the basic understanding. B equals mu H. Why did I say it's linear? Well, yeah, because it's basically a mu times an H equals a B. Now, in reality, when I say it's nonlinear, what that means is that as H gets bigger, mu actually changes. All right, and in fact, at some point, H gets to be so big that mu basically becomes like the material is air. All right, we're not going to focus on that, but I do have this thing where I say B equals mu H, and mu, I say, is mu relative times mu naught. And I wrote out here, I call that thing permeability, right? And I say that this permeability, I can define what its value is depending on what the material is. All right, so most of the materials that you deal with that are good magnetic materials have a mu on the order of about 1,000 to 10,000 times larger than air. All right, the permeability of air or the permeability of free space is this 4 pi times 10 to the minus 7 is the units on it. All right, this material I said the other day, which is a good magnetic material, this is called ferrite. So it's basically a combination of zinc and manganese is what this guy is. All right, it's ferrite. And depending on the type of mix that you get, the mu R is different. And you can buy different mixes, right? So if I'm going to design an inductor, and this is an inductor that's designed for a solar inverter, all right? If I'm going to design this thing, I will choose a mu R value to meet my application. And I'll wrap coils around it. And it's a delicate material, right? If I dropped it, it would shatter into a bunch of pieces. It's very close to a ceramic. Most magnetic materials are very similar to that, where they're like a ceramic kind of material. All right, but this is pretty common that I'll see some sort of a toroid like this, or the picture that we'll deal with later, you see these things and you see them in the homework where there's some kind of a material that looks like it has a C shape and it has a gap in it. Very often you get materials like that, all right, where it has a gap in it, and you actually choose the size of the gap, all right, to choose that. The gaps that we talk about are always very small, all right. One thing I forgot to do this picture, but you guys have seen the Tesla emblem, right, on the car. You know what that is? Part of the motor. It's a part of the motor, all right. It looks like a T, right? But it's a slice of the motor. I should have brought it up, but if you look at it carefully, look at it later, it looks like this, and then there's like a gap like that. This here is an air gap. All right, your problems in the homework have air gaps, but those basically is once you see it, you can't unsee it, right? But those gaps are very small. And looking at that Tesla emblem will give you a sense of how big those gaps usually are. And they're very specifically designed to get a particular B field. Okay, so we're going to get into that a little bit more, but all right, we'll talk through that as we go. Now, without going into again, I don't want to focus on the Maxwell's equations. I want to introduce them because they matter, and then get past them. Okay, there's how many Maxwell's equations? 4. All right, that's good. The 3 that matter here are which ones? Faraday's law, okay. Ampere's law. And then Gauss's law for magnetic fields. So technically there's 2 Gauss's law. There's Gauss's law for electric fields and Gauss's law for magnetic fields. All right, so Ampere's law. What does Ampere's law say in words? And the words can't be divergence or whatever. Current. If I have a current coming up through a surface, there's a magnetic field around the edge of that surface. Right? That's basically what it says. Okay. And those field lines are always closed. That's what Gauss's law tells us. This guy here, B dot dA equals 0. If I draw a circle like that, that means, what's that mean if I draw a circle in my integral sign? It's closed. Okay, good. So you remember some of that. So basically it says, if I had a cube of some kind and there was a magnetic field entering that cube, right? The total flux entering this thing has to be the same as what? The total same as the flux coming out. So if I got 2 lines of flux entering, I have to have 2 lines of flux leaving. That looks pretty similar to something else that you saw in circuits. Circuits 1, you saw that the total amount of charge coming into a node has to always equal what? Total amount coming out. It's KCL. This is a lot similar to KCL, right? And oddly enough, we made that parallel already to current density and flux density. All right, so we're going to keep going with that as we go through. Gauss's law is basically magnetic KCL, right? And the principle of, if I really wanted to get into this, the principle of conservation of charge, which there's some integral for that one too, gives you KCL. Right? I don't want to get too lost in the calculus, right? But that's certainly a result. So this is, yeah, like a magnetic KCL, right? There is a magnetic KVL too, which we'll get to, right? All right, Faraday's law, basically, all right, well, so it tells me that, right? Line integrals, tangential components, all that sort of stuff, right? So what does that thing say? E dot ds equals negative d by dt of b dot dA. The heck does that say? Right? So if I had a coil in a changing magnetic field, right? So if there was a field passing through that coil, what happens at the terminals of that coil? A voltage is generated. Voltage is generated. Yeah. And we talk about this, does it go against? Everybody gets lost in that kind of, does it go against, does it go with? I don't really care, right? There's a voltage that's there. All right. And is my sign wrong? Probably. But the cool thing about AC is I'm right half the time, right? So I won't worry so much about the negative sign. I'm much more focused on that basic idea, because that's a really core concept, right? So I want to apply these ideas, right? Ampere's law is the third one. We already sort of said what it is. I'm not gonna play with this guy too much, but what I did do out here is my right-hand rule, right? I think in some sort of weird British Commonwealth areas, they use a left-hand rule. Some of you might know that. I know there's a professor in the department that does it occasionally. So I'm not going to touch it. There's a right-hand rule, no left-hand stuff, right? Basically, what this says, what that picture is basically saying is that contour C is spanned by a surface S. So that hatching there is the surface. So the thumb coming up is basically, if I have a current coming through there, the fingers curl in the direction of the field. All right. So in this case, the field would be going around in a, what is that? It's a counterclockwise direction. Okay. All right. So the other day we talked about this idea here about magnetic flux. All right. So magnetic flux, I said, was B dot dA. And I showed a couple of different ways that I could orient this. It's a dot product, right? Basically what I've said is I got a B field, and then there's an area vector that I define for typically, people always show like, there's a square that can move itself, right? Well, what does that square represent? Well, typically at the edge of that square, there's a coil of wire, all right? I should bring this maybe on Monday, but I've got a coil from a motor in my lab, which if you look at it, a coil from a motor basically looks like this. Like if you took apart a motor, you would see a rectangular coil, right? There'd be a coil going around the edge of that thing. Okay, so most of the time, we're not going to deal with problems where we have to do the integral. Why would I have to do an integral here? If the B field is a function of position, so if B is not like B of X, Y, Z, right? If the B field's not a function of position, then basically this guy becomes B dot A, like that, all right? So if I, and again, B dot A, a dot product is a scalar number. How do I compute that scalar number? So, and be careful about that. Magnitude of B times magnitude of A times the cosine of the angle between them. Now, what I did here was I showed what we create a n hat vector, a normal vector, which is where the area vector would be. So if I talked about this guy, let's say this thing here had an area that was 2 meters squared. So how would I write the A vector? If the area of that coil was 2 meters squared, yeah, 2x hat, like that, right? And then the B field is, I don't know, let's say in this case it was 3x hat, okay? Right? So what would the flux be in this case? Yeah, phi would be equal to 6. Okay. What about in this? And I did this the other day, right? I took 2 coils. One coil was making the B field, and the other one was receiving it. We're going to look at that again later, right? If I turned that thing 90 degrees, we saw that there was no voltage, right? But I don't want to take that step too far. How much, in this case, same coil is now turned 90 degrees. So what's the n hat in this case? So if I said, here's my area vector, what would my area vector be in this case? Or it's the same coil. It's got the same area, right? What would you say?
The area times y hat.
Yeah, so 2 times y hat in this case. So I have, if I want to get the flux in this case, it's phi equals B dot A. What's that equal to? I got an x hat times a y hat, right? That gives me a 0. There's no flux passing through that coil. It kind of makes sense because if I think about that coil turned, all the B field's missing it. All right, if I turn it at some angle, then it depends on the cosine. So in this case, this guy would, the magnitude of B times the magnitude of A times the cosine of the angle between them. All right, so let's say that they're turned so that this angle here is 45 degrees. What would it be then? Yeah, so my B was 3, so I'll say 3 times 2 times the cosine of 45 degrees. Yeah, so it'd be root 2 over 2, right? All right, that's kind of the key thing. Now, what's going to happen in a motor is that theta, that angle, is going to become a function of time, right? Because I'm going to make the motor turn. So the motor's going to turn, means the coil's going to turn. All right, when the coil turns, theta becomes omega t. Okay, that's for later. The important thing is that you understand this relationship between sort of the direction of the flux and the orientation of the coil, right? So you got a problem like this. It's a numbered problem 7 on the homework. Now I take it one step further on the homework and I ask you to compute the voltage, which we'll swing back to in a second. All right. All right. Now, a really important concept is if I have something like this guy here. All right. Now, first of all, this guy is I guess he's an inductor, but he's got 2 coils. Maybe that's hard to tell. It just looks like 2 crappy windings, right? This guy has 2 coils, which means he's a what? Transformer. Now, what if I took the 2 coils and connected them in series? Then he's back to just a single inductor, which would be 1 inductor plus the other one. If I have inductors in series, right? They sum. Okay. All right. Here's what this looks like. So if I were to look at this thing, in other words, if I took this guy from the perspective that you're looking at, right? That's basically what you're looking at here. I've got a bunch of windings like this. Now, if this is a basic C core, a very common shape to have, we really exaggerate this. That G is very small. Again, look at that Tesla logo and see how skinny the gap is between the top and the bottom. It's very small. All right. Usually it's on the order of in practice, maybe somewhere on the order of like 5 mils. All right. Who's ever heard of the unit mil? What's a mil? 1,000th of an inch. A mil is not a millimeter. A mil is 1,000th of an inch. Usually those gaps are on that order. All right, so I'll show you. I'll bring in a C-core and I'll close it together so you guys can see. You can see through it, but it's very small. All right, this really is exaggerated when you look at it, okay? All right, so if I have a coil with N turns and I put a current I into this guy, all right, there is going to be a flux that goes through it. All right, so in this case, I just said I'm not going to worry about where the fields are that are created by that current. And I'm not even going to actually worry about that current for now. I'm just going to say I got a flux phi going through that coil. Came from somewhere else. Okay. Now, if I look at this, I basically have, and maybe looking at this sort of helps, but basically what I have is basically N little planes of wire that are sort of stacked on top of each other. All right. So each one of these guys has a flux going through it phi. So phi is the flux through each coil. In other words, each coil has the same flux going through it. Sometimes, though, what we do is we say, what's the total flux linking the entire coil? All right, so what I do is I say, well, you know what? I'm going to add that up, and I'm going to say the total flux linking the entire coil is there's a flux. So phi goes through the first coil. So the first coil would be the bottom one here. Phi also goes through the second coil. And it goes through the third coil. All the way up and until I get to the nth coil, like that. If I've got N coils, what's this become? Yeah, N times phi. Now, at first, it always seems kind of weird that we define that. All right. But one thing we're gonna get to, and it's kind of an important idea, is if I had an inductor, there's a flux in that inductor, right? And what do we know about if I write d flux by dt? What is d flux by dt? You're right. Erase the electric field. This was one of and this is why. So Faraday's law is basically this guy right here. I have Faraday's law tells me that if I have a coil and there is a changing magnetic field going through that coil, then there's a voltage created. If I'm a fields person, I'll say E dot ds equals negative d phi by dt, right? This is phi. I'm not a fields person. So I just like to think of it as d phi by dt is equal to what? Equal to what? So what did Faraday's law tell me in words? Because you guys get lost in the calculus pretty easily, right? If I have a coil and there's a changing magnetic field going through that coil, what do I have at the terminals of that coil? A voltage. So the rate of change of flux through that thing is equal to V of t, which is what E dot ds is equal to. All right. So if I have that, right, d phi by dt, the rate of change of flux is equal to voltage. Okay. So when I look at that picture right there, where I have basically all of those coils stacked on top of each other, if I looked at any one of the coils on this inductor right here, right, and I were to cut that wire, there'd be a voltage on each individual wire, right? So this is kind of like if I have N turns of wire, it's really like I have N inductors in series with each other, right? So if I think about this, then if you had, first of all, what's the voltage for an inductor? The voltage on an inductor is what times what? L di dt. All right. Somehow that's got to be related to this d flux by dt. Right? Because if I have just a single wire like this, right? There's a voltage at its terminals if there is a field going through it. All right. So basically, V equals L di dt comes from d flux by dt. This right here applies to just one coil of the N, right? So if I had N of these things in series with each other, which I do, right? What happens if I have a bunch of inductors in series with each other? They add, right? So basically what I say is that I have L1 plus L2 plus L3 all the way up to Ln times di by dt. Now, we can show this pretty easily, but what do you think is true about the inductance of each one of those coils individually? They're all the same, right? So basically what this becomes is N times, if the flux through any one of them is d phi by dt, the flux linking the entire thing is N times d phi by dt, right? Because there's basically, if d phi by dt is the voltage on one coil, if I have a bunch of coils in series, I add the voltage of each one. So it becomes N times what it is in any one of them, okay? So we write that as d lambda by dt, like that. So so basically V equals d phi by dt is true for one turn. V equals d lambda by dt is true when I've got an n turn device. And almost always I have an n turn device, right? Which means that I have to usually figure out the flux linkage. All right. It always gets confusing for people. I think, like, what the heck is flux linkage? How is it different, right? But if I have an n turn coil, it makes sense for me to figure out what it is for the entire coil. All right. So what we say, the definition that we make, right? So V of t is d phi by dt, or n times d. So sorry, V of t is d lambda by dt, n times d phi by dt, or L di by dt, which tells me that lambda equals Li. Now that's exactly like if I have a capacitor. I put a voltage on a capacitor that has a capacitance C, and the amount of charge stored on that guy is Q equals C times V. So you store charge on a capacitor, you charge up a capacitor. On an inductor, what do? You put a current into it. So notice the parallel. Q equals CV, lambda equals Li, right? I put a voltage onto a capacitor, I store a charge. Put a current into an inductor, I store a flux, right? That's the basic way that it works. We don't say that that we charge an inductor. You charge a capacitor. What do you do to an inductor? You don't charge it. You magnetize it, is what you say. You magnetize it. This guy stores a magnetic field. Okay. So we magnetize an inductor is the term. All right. So it's very similar to a capacitor. Capacitors make sense. You learn a lot. Why do you learn so much more about capacitors? Because you do. Electronics 1, electronics 2. Did you ever see an inductor? Never. Well, no. Well, what's small? What form factor? The form factor of capacitors fit onto chips easily, right? And so electronics is typically taught by chip guys. Inductors don't fit onto chips as well. Now, they do, right? There's chip inductors in your phone, probably, but they're not common in most circuits. The other thing is, unlike a capacitor, Q equals CV. For pretty much any capacitor, Q equals CV always. For an inductor, the inductance changes if the I gets to be too big. All right, so that relationship, lambda equals Li, is kind of breaks down fairly easily. So they're ugly to deal with. All right, so there's a couple of reasons, but inductors are really important in motor operation, generator operation. So we got to focus on them. All right. So let's say we want to create an inductor, just like I did here. All right, I want to figure out where the fields are going to be inside this thing. And I want to talk about the approximations on the geometry, because one of the problems that always gives people problems, and that was probably directly related to your question that you put in Discord, Cody, is the approximations about the geometry or why you're getting your answers wrong, probably, because the approximations are important when we deal with this stuff. Okay, so what I have here is basically this guy, right? Except I only got one coil on it. It's got n turns. And I guess I didn't write this here, but I'm just going to say this guy has a mu value that's mu, and I'm not going to use a number for it. It's just mu. Okay. And let's say that the mu is much, much bigger than mu naught. Okay. And much, much bigger than probably means it's 1,000 times bigger or 5,000 times bigger, something on that order of magnitude. Now, this core has a diameter, W, so I marked that out here. And I said it has a radius R, which is measured to the center of the core, okay? And I've said that, what does this mean here? The radius is much larger than W, all right? What is much, in fact, much, much larger than is, I guess, what I said. What does that mean? Well, it means it's much bigger than. So what does much bigger than mean? Well, yeah, so in my mind, it usually means it's at least 100 times bigger, such that maybe W can be considered to be 0 in some cases, okay? So I'm going to basically say it means it's at least a factor of 100 different, probably. All right. So, all right. So basically what I want to do is I want to use Ampere's law to try to figure out what the H field is going to be. This guy's an inductor, right? So I'm going to basically, if I want to figure out the inductance, my basic approach, well, let me not jump ahead to that. I want to figure out what the magnetic field is going to be. Let's just start there. So I use Ampere's law. I wrote down what Ampere's law is. Okay, I wrote down what it is, but what is it? What is it in words? I care more about what it is in words. If I see you on the street in 10 years, you won't be able to recite that at all. But you might be able to tell me what Ampere's law is, right? What is it? What's that say in words? Yeah, current through a surface creates a magnetic field around it. Perfect. All right, so here's my current. All right, so I got a couple of different places where I can draw the surface, and basically I look at this like I've got 3 choices for that surface. Now again, what I'm looking at is basically a top view of this thing. All right, so I'm basically looking at this guy straight on. So the way that I think about this is, so if I have a current that goes into here, right? That current's going to go into the wire. It's going to make a turn and come up at you here, go over, then go down, then go over, come back, go over, go down this way, right? So the way that we draw this is I've got a current and the way there's a current going into the page here, then it wraps behind, and then it comes back out of the page, right? And then it goes this way again, and then into the page, and then out of the page, right? So if I draw that, how do I do this into the page, out of the page stuff? How do we denote that? So X means what? Into the page, and a dot means out of the page. It's like you're looking at an arrow coming at you, right? That's what the dot means. So basically, here's the way I set this up. All right, so I have out of the page on the outside of this thing, and I have into the page on out of the page on the outside, into the page on the inside. All right, now I've got a couple of different places. So I basically said, all right, the total current going through a surface gives rise to an H field around the outside. Man, I didn't delete that out. I said it's 0. It's 0. Why is that 0? Why is that equal to 0? I don't know what that means. I'm too dumb. Yeah, what you said might be correct, and what I said might be correct too. But the net current coming through that surface is 0. How do I know that?
Current can't stay in a surface.
Well, so it's the net current coming through a surface. So think of this tabletop as the surface, right? So I got a current. So when I have a dot there, it says the current's coming out. When I have an X, it says the current's going in. So it says here, I put 5 turns on this thing, right? So I have 5 times I coming up. And what do I have on the other side of the inductor? Negative 5I, right? Because directionally, I got 5I coming out, negative 5I going in. So I got 0 net current going in. So how much field is going to be around that edge of that surface? 0. All right. So there is no field out here. H equals 0 out here. Okay. Now I'm going to do it like this. Right? I'm going to put this surface. All right. How much current goes through there? 0. There's no current penetrating that surface. All right. So if there's no current penetrating that surface, there's no field on the inside. So that means there's no field in here. So H equals 0 in here. All right. I got lots of choices for my surface. Let's say I do this one now. All right. What's the net current going through here? Well, it's N times I, right? I've got 5 turns of a current coming. Which way are they penetrating through that surface? Are they going in or out? They're going into the surface, right? Not out of the surface. So I have N times I, so that means there's got to be an H field going around that thing. Now, with the way that I've drawn this guy, how do I figure out the direction that that H field is going? Right-hand rule. So in this case, I got my current going in, right? So I guess I got to stand this way. So I got my current going in. My fingers are going to go this way, right? So it's going to go around the edge like this. All right, that's where my H field's going to be. Now, this could get complicated, right? This guy is H dot ds equals J dot dA. This calculus could get complicated unless I make an assumption that R is much, much less than W. Much, much bigger than W. All right. If R is much, much bigger than W, then I can kind of assume that W is pretty close to 0. So it's just like a circle, which means that the variation in the H field from the inside of the donut to the outside of the donut is basically negligible. All right. And I'm going to assume that the whole donut is sitting basically right at the center of the donut. So, well, not the center of the donut, but the center of between the inner and outer diameter. All right. So what I'm going to do is I'm going to solve out this guy, and I'm going to say for this choice that H, and I can say it's H phi like that, dot ds equals Ni. Why did I write H phi? To make the fields guys happy, right? Which direction is it going in? The phi direction, right? The circumferential direction, right? The phi direction, right? So in this case, it's super simple because that if I assume that the entire donut is located right there at wherever the radius is, then there is no variation with respect to position. And so it would be H phi times the length, right? What's the length of this curve C here? 2 pi r. Now that wouldn't be true if this dimension mattered. In magnetics, we usually make the assumption that it doesn't. All right. And as long as we get our geometries right, those assumptions are good. Okay. That equals Ni, and I end up with H phi equals Ni over 2 pi r. So I like to do a units check. What did I say are supposed to be the units on this thing? Amps per meter. Are they? Yeah, because I've got amps over a length. Okay, so that's good. Now, let's say I want to get B, the B field inside there. What's the B field? Multiplied by mu. Yeah, mu times H. So this becomes mu Ni over 2 pi r. Now let's say I want to figure out the flux, because this is the flux density, but I want to figure out the total flux that is going through this core. So in other words, this toroid, right? There's a flux in the core of this toroid. And I know the flux density when I know B. But this thing is, as you guys identified, it's an inductor, right? So what do I want to know? At the end of the day, I want to know what's the flux in here and what's its inductance, okay? So first step is to figure out the flux. How do I figure out the flux? I know the flux density. So how do I figure out the flux? Yeah, look at the surface. So surface integral B dot dA, right? So which is, if my B is constant, not a function of position, simplify that integral for me. Exactly, right? And in this case, they're going to be perfectly lined up with each other, B and A, right? Because if I think about where's the A, this is the important thing. Where's the A that I'm talking about? Well, so the H field, the field is going this way, we said, right? So it's going to be circulating around here like this. So as it moves, it's moving this direction. Which area is it cutting through? The cross section, right? It's going through here, so it's cutting through the cross section, right? So think of the H fields going that way, right? So the area that it's cutting through as it moves is the cross-sectional area of this guy. So the H field, basically, if I look at it like this, it's going this way. So the area that it sees is the area of this guy. So the cross-sectional area of the core is pi times the radius of that thing squared if I drew it circled like that. So what would that be in terms of the variables I've given it here? Pi times r squared. What's the radius of this thing? W over 2 squared. Well, something that's going to bother some of you guys is I just ignored W before and now I'm not, right? Because it mattered here and it didn't matter there. All right. Usually what we do in magnetics is we are making the approximations that make the calculus go away. And we need to make sure that those make sense in reality. But for a device like this, those approximations end up working pretty well. All right. So in this case, what do I end up with? I end up with that phi is equal to B times A. So that's mu n I over 2 pi r times pi W squared over 4, like that. All right. So this guy becomes simply what? If I simplify it down, mu n W squared over 8r, because the pi's canceled. Okay. And the I went there. I like putting the I next to it. Okay, because if I look at that thing, right, lambda equals some, or sorry, phi equals some stuff times I. If I look at that thing, what's true about all the stuff multiplying the I? Well, it's actually not quite it's the inductance of a single turn. All right, but they all depend on the properties of the material or the geometry of the material, right? They're all constants. Whereas I is a variable, right? I could put in 1 amp, 2 amps, 3 amps, whatever. All those things are constants. Okay. Now, let's say I wanted to get the inductance of this whole thing. How do I get the inductance of the whole thing? There was one step before I got to the inductance, right? Flux linkage. This is the flux going through the thing, but I said that flux goes through one turn, then another turn, then another turn. Yeah, so basically lambda equals n phi or n squared times mu W squared over 8r I. Lambda equals Li. So L has to be n mu W squared over 8r. Like that. Exactly. Yeah. The inductance only depends on the geometry of the geometry and the material. So the construction of it. Yeah. Right. It's a simple way of saying it. It depends on the material and depends on the geometry. Okay. And the number of terms. That should be an n squared. Okay. It's always going to have an n squared too. So n is a unitless number, right? It's the number of turns. Turn is not a unit, right? So it's always n squared. If you end up with n, you did something wrong. Okay. So it turns out there's a simpler way of doing this, and it all comes down to sort of one thing. Why? So we did, this was our process, right? And you're not going to follow this process too much. We're going to use a different approach, but basically I get the H field, get the B field, get the flux, get the lambda, get the L. Now we're going to follow this, basically picking it up from where we get the flux. But I wanted to draw a parallel for a second and say, all right, let's say I did this. Let's say I had a battery, all right? And you went to the lab, or I don't know, let's just say you went into the lab and you had a voltage source, you had a power supply, and you hooked a resistor up, right? So here's basically 12 volts across my resistor. All right. Where are the charges in that circuit? Where's the current in that circuit? Yeah, it goes, well, yeah, well, why doesn't it go here? Why don't the charges move here through the air? Well, yeah. So in other words, the conductivity of this resistor is way less than of the wire. I'll say the conductivity of that copper wire is much, much less than the conductivity of air. There's a factor of 10 to the 12 difference between copper and air. So as a result, the charges all move through the wire. You take advantage of that all the time. If that wasn't true, you'd have to do Maxwell's equation every time you analyze a circuit. Every single time, right? It would be a mess. All right, so you don't want to do that. And we don't have to. We make use of electric circuit models where I say V equals IR and all that stuff. V equals IR is an approximation. The reality is that I've got an electric field source and I got current densities and all sorts of stuff, and I really should do Maxwell's equations, but I don't have to. I can make it an algebraic problem because of the fact that they don't cut through here, right? And all the charges stay in the circuit. Same is kind of true here, right? So let's say here's a surface that I could have drawn, right? So I drew this oval surface, right? There's no reason why I couldn't have drawn this one. Why is this one? There's a net current going through this one, right? Is there not? There is, right? Why do I think I'm using my brain when I draw my surfaces? Some things I know. Why? So if there's a net current coming through here, so there should be an H field around the outside of it. Why is there not a field here? Why is there not a field in the air? In other words, we basically said, you guys made an assumption that you didn't even really think about, right? You basically just said to me that the H field that these wires created just stays inside this core. Why is that? Why didn't it leave? Why don't I have an H field that goes around that oval? Because we don't want to calculate it. Exact. So it's not epsilon, but the mu of the core is much, much greater than the mu of the air, and the mu of the air is equal to mu naught. All right. Because of that, right, the B field stays inside here. Now the difference between conductivity and permeability is pretty different. Some of the field, as we'll talk about, does actually leave the core. Not a lot, but some. There's pretty much no charges leaving a wire and just kind of meandering through the air, right? But for a first approximation, when we first start learning this stuff, if our mu is a couple thousand times bigger than that of air, then this is more or less true. And that means that all of the field stays inside of the core. So when I think about this, I drew a circuit model for this thing. The model was, I don't have to do Maxwell's equations, because I can say I have a voltage source and a resistor, and these wires exist to conduct the charges over to that resistor where they do work. The same thing's happening here, right? What's going on here? In this case, and let me use a term here. So there's a term that you learned for voltage, right? It makes charges move. Yeah, so we call this EMF, all right? Electromotive force, all right? What's going on here? Well, some current creates a flux, and that flux moves through a core. Here we had a voltage source that moved charges through a resistor. Here, well, and I should say it moves charges through wires, right? In this case, what I'm doing is I have current creating a flux through a core. So what I can do is I can make this parallel. All right. The parallel I'm going to make, and again, you really want to get into this, basically KVL and KCL come from Maxwell's equation, simplifications of them, right? KVL tells me the sum of the voltages around a loop is equal to 0. All right. Ampere's law tells me something similar. Basically, it says that the sum of the magnetomotive forces around a loop equals 0. All right, so the parallel I draw here is a voltage or an electromotive force makes a current move through a wire. In this case, we say is a magnetomotive force makes a flux move through a magnetic material. All right, and so what we do is we draw this parallel here, right? So an electric circuit, I have an EMF or a voltage that pushes current through a resistor. In a magnetic circuit, what I have is a magnetomotive force, or MMF. So basically, it's N times a current. That creates a flux. That flux moves through a core. So the way I do it, notice it's the exact same thing. So an MMF is my source. My current is a flux, phi, right? And my reluctance is, I use this script R to do it, all right? And all of the Ohm's law, KVL, KCL applies the same way. Right? KVL tells us that the sum of the EMFs around a circuit is 0. KVL here tells us that the sum of the MMFs around a circuit is 0. And then the fluxes at a node equals 0. That's KCL. Reluctance is like magnetic resistance, yeah. And so we can determine what it is. I'm not going to get through the derivation of it here, but basically, for a resistance of a wire, if I have a wire of length L, the conductivity sigma, and a cross-sectional area A, right? That's how I get the resistance. L, the length, right? So just to be clear, so it's, if I had a wire like this, its length is L, has a cross-sectional area A, and a conductivity sigma. Same thing is true. If I have a magnetic material with a particular length in a particular cross-sectional area, I can define its reluctance. All right. So I want to go back to this problem. All right. So I want to use magnetic circuits instead. So what do I have to do here? So basically, I got to find what the MMF is, find the reluctance, and then find the phi using the circuit model. In other words, I want to turn this guy into a magnetic circuit and say, here's the reluctance, here's the phi, here's the MMF. All right, so what's the easy part? Finding the MMF is pretty easy. What's the MMF? Ni. All right, we're done with that. What's the hard part? The only hard part is actually finding the reluctance, and it's not that hard. But what's hard about it is figuring out how to do that. So the formula for the reluctance, it's the length that I go through divided by mu times the cross-sectional area. Okay. What's the length? So it's basically the length that the flux would move through. Yeah, basically, again, with this approximation that R is much, much bigger than W, I basically assume that it's going through that right at the center of this thing. So basically, my length is 2 pi R. Okay. What's the cross-sectional area that it's cutting through? Yep, pi W over 2 squared, or pi W squared over 4, like that. Okay. So if I jump ahead here, I'll just do it all right here. So if I plug those in here, what's that going to become? I'm going to get a 2 pi r on top. Right, and on the bottom, I'm going to have a mu times pi w squared over 4, like that. So my pi's cancel, right? And I end up with, for this guy, here's my MMF, here's my NI. This reluctance was, what was it? Yeah. 8R, right? So if I look at this guy right here, right? 2R over mu w squared over 4. The 4 is going to go up top, right? So it's going to become 8R over mu w squared. This guy becomes 8R over mu w squared, like that. So let's say I wanted to figure out what the flux is here. Well, flux is like the current in this thing, right? Yeah, so phi is MMF divided by the total reluctance that MMF source sees. So that's basically 8, Ni divided by the reluctance, which would end up being N mu w squared over 8R times I, right? So if I wanted to figure out the inductance, what do I need to do now to find the inductance? Get the flux linkage. So how do I get the flux linkage? Not quite. How do I get the flux linkage? I got to multiply by n first, right? Right now I just know the flux. So I know lambda equals n phi. So that would be n squared mu w squared over 8R times I, like that. Where's L in that whole thing? Yeah, the coefficient on the I. Right now, if the thing I should do now is I should compare. So this was our process, right? To use magnetic circuits, get the MMF using the current, get the reluctance based on the geometry, get the flux using the circuit model. So you basically at that point use circuit analysis tools, all your KCLs, KVLs, voltage dividers, current dividers, all that stuff to figure out phi. Lambda equals n times phi, the flux linkage. And then I can use that to find the inductance. Now, one thing I notice, sometimes I don't like to plug in all the numbers because when I do it, you sometimes lose this. What I see here is that my L value is always n squared over the reluctance. All right. It always should be n squared over the reluctance. That's a good check to see at the end if you've gotten things right. Okay. All right. So if I look at this, then we basically took 2 approaches, right? So this was I got lambda equals mu n squared w squared over 8R times I. This is when we did Maxwell's equations over here. This is the exact same thing that we got when we did magnetic circuits. No calculus, right? No. We didn't do any calculus here per se either, but it sure looks ugly, right? Whereas this is fun, happy stuff, right? Because this is things that we should all be comfortable with. It's just straight up algebra. All right. So, all right. All of the magnetic circuits, just like electric circuits, right? Basically, reluctances combine like resistances. So if I have 2 reluctances in parallel, I take 1 over, 1 over, 1 over, right? So in parallel, I'm not gonna be able to say that nicely, right? This is R2 and this is R1. You would say that R equals 1 over R1 plus 1 over R2, like that, right? They're in series, you add them. KCL applies to fluxes, KVL applies to MMFs. All right, so it's the exact same thing. Just think of MMF as being the voltage, flux as being the current, reluctance as being the resistance, and we don't have the others. We don't have capacitors or inductors. You just have resistors, voltages, and currents. It's just like circuits 1. There's nothing too hard about it. And we're not going to do weird magnetic circuits, right, with supernodes or whatever. We're not doing that. It's going to be fairly straightforward. The one you have in the homework is about as hard as they could ever get. And it's a pretty basic circuits problem. So when we do these problems, this is basically the steps, right? And problem 5 in the homework is just like this. I get the flux paths, get the circuit model, get the reluctances, get the MMFs, get the fluxes, get the flux linkages, get the L, right? It's very mechanical sort of process. All right, so let's say I had this character here. All right. So first step with this guy here is if I look at this, my step 1 was to get the direction of the flux. Now, first of all, if my mu, let's say again, my mu is much, much bigger than air. Right? So that means that where's the flux going to be? If my mu is much, much bigger than air, where's all the flux going to be? Inside. Right? Now, when it gets over to this gap, it's going to jump the gap. And like I said, as long as the gap's small, it's going to jump right across. If the gap's big, it's going to do a lot of what I call fringing. It's going to kind of go around it. I don't want to deal with that because that's a little complicated to deal with. I'm going to think of that gap being real small so that most of the field just jumps right across it. Okay, so what's the direction of the flux? Okay, so how do you get that it's clockwise? Right-hand rule. So the way I look at this, I got the I going that way. So I put my thumb in the direction of the current. And so my fingers curl around. So that tells me that the field would go right up through the middle of that guy, right? So my flux is basically going that way, like that, okay? Now, I want to draw the circuit model for this guy, all right? How many sources of MMF? How many magnetomotive force sources do I have here? 1 coil, right? So this guy, if I were to draw out the circuit model, so we did the direction already. We said phi goes that way. Step 3 was to get the circuit model, all right? So I have a magnetomotive force, and it's going to draw a current going out like that. So I'm going to call this guy, there's a phi here and an Ni here. Now, flux lines are always closed, so the circuit better be a circuit. In other words, it better be a circle. Stuff leaves, stuff comes back, right? So how many reluctances are in this circuit? 2. All right, 1 is the core, R core. The other one is the gap. I'm going to call it RG. Now, why don't I just have 1? Why are they different there? What's that? Different permeabilities, right? What's the permeability of the gap? It's air, so it's mu naught, right? Whereas this guy is, I said just mu, right? There's 2 different materials. Now notice, in this problem, that means I got to define what RC and RG are. So RC is this character right here. So what would RC be? So notice what they did here. Now, technically, there's probably some there is calculus that you really should be doing to figure out that length. I am making the approximation. When I do this, I am making the approximation that the B field is constant across the surface area inside this thing. All right. And I'm also making the approximation that, just like I did with that donut, where I basically said my donut was so skinny it was just a circle. What am I making the approximation of when I look at this sort of C core here? Okay. It's right. All of the material is located right at the middle, right? And so in this case, I'm going to say it's the length of the core, right? Is the length that I'm traveling through over mu times the area of the core, which here is 12 centimeters squared. Now, to be clear, I think I gave you stuff in centimeters as well in the homework, right? We're supposed to do everything in SI units, right? So centimeters squared, how many meters squared? So 12 centimeters squared, how many meters squared would that be? 0.0012 meters squared. Right, and you can do your unit conversion to see that that's right, hopefully. All right, now what if I had to do this guy, the gap? So RG, The reluctance of the gap would be whatever the length of the gap is. Usually I call that G. So in this case, this is G, the 0.05 centimeters. No, it's 0.05 centimeters. It's small. Okay. Divided by what? U naught over A. And A is still the same. Right? A is still 12 centimeters squared. Yeah.
So the reluctance of the gap is going to be much greater than the core.
The reluctance of the gap is going to be much less typically than the reluctance of the core.
And mu naught is smaller than
Because mu naught is sorry, RG is going to be much bigger. Because if you think about what in an ideal world, and this is what I wanted to be able to show too. In an ideal world, the core is just like a wire. The wire you ignore, you don't think of the resistance of a wire. Just like you don't think of the reluctance of a core. The job of the core usually is just to direct the flux to where it's useful, like in the gap. All right, same thing in that Tesla motor, right? The iron just directs the flux into that gap where it's useful. Okay. All right. If I want to figure out the phi in this circuit, how do I figure out the phi? How do I figure out the phi? Yeah, it's the Ni divided by the reluctance of the core plus the reluctance of the gap. Now I put some numbers in there. I don't want to, right? How do I get the flux linkage? Yep, it's N times phi. How do I get L? L ends up, so this guy is Ni over reluctance of core plus reluctance of the gap. I get, and this is N squared when I do it that way. That tells me that my L is what? N squared over the reluctance of the core plus the reluctance of the gap. Okay. And usually by controlling the gap, I can control the inductance. It's usually how we try to do this. Okay. All right. Now, how do I approach? This is more similar to what you got in the homework, right? So what did I do? I got a lot of stuff here, right? So what I like to do is, first of all, I would figure out where is the flux gonna go. That's step one. Where is the flux gonna go? I got to do right-hand rule, right? So I current going that way. So I put my thumb in the direction of the current. That tells me a flux is going to go up, right? Through that thing. Now, once it gets to so there's a flux phi that's going to go up through here. Where's it going to go? Once it gets to some of it's going to go here, right? There's a flux that's going to go here, and there's a flux that's going to go here. Right. All right. So let's think about it this way. In my mind, I say I have Ni. I like to draw them next to each other. Then there's a reluctance to this middle piece, isn't there? And then, so let me get rid of the field pictures. There's a reluctance here. And there's a reluctance here, and here, and here, and here, and here, and here, right? And so if I have three reluctances in series like that, what do they become? One reluctance. So if I wanted to solve for what's the total flux here, what do I have to do? I could do KCL or what if I wanted to, or I could say I've got this reluctance and that reluctance in parallel with each other, combine those, right? And take whatever approach I wanted to take to get that phi value. The phi is the flux going through the coil itself, right? I don't care what the flux is through these other legs. I care what it is through the center leg, through the coil. Yeah.
Before we combine all of these, we obviously have to calculate.
We did a calculate. So let's talk about calculating one of them, right? So what we do is we always think of it like this, all right? Always think of it like this. Everything is located sort of at the centers, right? So let's draw it like that. Everything's located at the centers. All right, so let's talk about just like this side right here. So this, how would I get for this side? What's the length going down that side? Well, I'd go from this point to this point. So what is that? What's the length on that side? Yeah, so it'd be 16 centimeters plus 2.5 plus 2.5. Like that. Okay. What's the area, the cross-sectional area that I would go through going down that side? Well, it told me the depth is 5 centimeters. That means this guy's 5 centimeters deep into the page. So what's the cross-sectional area that I go through? Well, so it says it's 5 centimeters wide and 5 centimeters deep. So the area is 5 centimeters by 5 centimeters. Right? So it's 5 centimeters wide. That's what this is. And it's 5 centimeters deep. That would be down into the page. All right. So let's say I wanted to do, let's just do, how about this middle guy here? The middle guy would be exactly the same, would it not? And so would this one, right? What else would be the same? This and this and this and this would be the same. This, and this would be the same. I could put all those, you can then kind of think about all those being in series in parallel. Now I'll say one thing real quick. I'm over time, but one thing you're going to see in the homework, right, I think is you have a gap here. Now you can get real anal if you want to. And you can say, well, the length goes from here to here, and then I skip over there. You don't need to do that. I make an assumption in there. I tell you this. I basically say, assume that the gap is so small that you can neglect it. If you do that, it'll work.
So that gap won't have
Won't have an effect. Right? Won't have an effect. You could be anal about it if you want to, but the thing with magnetics, you don't have to be. Now, if that gap is big, it's probably a crappy inductor anyway. Right? So if I made a good inductor, my gap should be small. All right. So I'm gonna stop there. You bring your question up to me.